today, so this is my great pleasure to come here in Amsterdam, and I wanted to talk to you about one of them is, mostly I want to talk to you about what you should expect in Spark 2.4, which is due to come. You don't like it? That's art. Okay. I might need someone who hold the plug for the rest of the talk. Okay, so I will talk about what you should expect coming in Spark 2.4, and also a little bit about the MLflow. So some people got here an introduction during GoDataFest, but I want to show you what it looks like a bit in practice for the people who haven't seen it. And in particular, I would like to show you hopefully some of the features I'm the most excited about in coming in Spark 2.4, which are really about combining the world of AI and the world of distributed big data. So I've been using Spark for quite a while. I think I'm the second user of Spark, and now you might think it's pretty, like you might think it's hard to use Spark, but back then, when you wanted to use it, you would have to send an email to Matti Zahari, and then he will answer to say, hey, here is a zip file, good luck with if you want to use it. By the way, you should figure out it contains C++ code, and then good luck on that. So I can tell you it has definitely improved a bit since then. But mostly I've been working at Databricks on improving the environment around deep learning and on helping how to build better machine learning solutions around Spark. So I don't know if you have a microphone, but I guess we should also be able to take some questions during the talk, and I can repeat them, right? Okay, so we'll chat a bit about some of the most exciting features coming in Spark 2.4. Then I'll talk a little bit more about Project Hydrogen, and then finally about how MLflow can integrate and help with the simplifying and accelerating the machine learning lifecycle around Spark and other machine learning tools. So just to have a quick show of hands, who here is using Spark? Okay, everyone. And who is using Spark 2.3? Okay, everyone. So who is using older version of Spark? A few people. Spark 2.2. Okay. Okay, so not too far. It's so here's what you should here's what most of you should expect different, and the answer is going to be essentially from the APIs you're using pretty much nothing, and what I'm going to talk about is really some of the new things which are being ported into it on top of performance improvements. So it's not available yet. I think a release candidate was being voted on yesterday and today. And I am not sure if it is going to be accepted. But in any case, it is going to be released soon. So in a matter of weeks, definitely less than a matter of months at this point. Sorry? Yes, yeah. So it's okay. So it was voted down eventually. So some of the biggest changes is probably if you're using Spark on premise or on your own cluster, this is going to be the support for Kubernetes. So already in Spark 2.3, you could integrate Spark with Kubernetes. So Kubernetes, for the people who are not familiar, is a framework from Google allowing you to manage easily fleets of machines, and by leveraging the container systems on top of that. And the whole idea was to be able to directly use Kubernetes for scheduling your machines and asking Kubernetes to manage all the infrastructure for Spark. Spark being then just responsible for talking with all the containers containing the executors and not having to figure out more about and just being able to discover the environment from Kubernetes. So this simplifies a lot the setup for a number of people who don't want to use Yarn or another scheduler. In particular, with Spark 2.4, it is going to be more relevant in the sense that you can directly use on the same Kubernetes deployment not only the Spark and other application, but also you can also use some Spark application on top of that. So now you have within Spark, you have better ways to directly submit some jobs or have interactive applications. In particular, this is what the client mode is going to offer. And Kubernetes actually, it's much more complete than simply managing some clusters for you. It also handles sharing secrets, sharing security, and handling security, and also mounting some data sets and sharing data across different machines and different containers. And Spark will also leverage some of these capabilities to access the volumes through that. So if you are running Spark on-premise, this is going to help you significantly if you already have a Kubernetes deployment. And I think for now I think that the support is being rolled into Spark, and I suspect that in the next couple of months we're going to see more and more applications built on top of that, especially I think around Jupyter and Spark. Another topic which also was has been also pretty much expanded compared to Spark 2.3 is the support for higher level functions inside the SQL syntax. So this is so if you don't know about the syntax, essentially it's a way to write some small functions directly inside your SQL command, and this is an extension to the SQL syntax. So here, for example, it allows you to take arrays inside some columns and express some operation that you would have in Scala or Python, for example, for zipping. But you have many more. So now actually you have a very rich collection of these functions, of these high-level functions. Now you can also do general transforms. You can do reductions. And you have also access to the usual operators, such as does an array contain an element, or does it have no element, and so on and so on. So this covers a lot of cases that people used to write typically with Scala UDFs or Python UDFs, and before you had some performance problems because Spark was not necessarily aware of what your query would do, and all it would see is a Scala blob coming to interact with the content of a column. And now the SQL optimizer Spark Catalyst will have directly access to the function that you're trying to write here. So Spark can directly optimize and write some dedicated code directly inside the optimized version of your code to replace that. So we have seen already some significant performance improvements for people who are switching to the syntax. So it is a new syntax, but it is worth the costs of switching to it if you are having some performance issues for a lot of tiny user-defined function in Scala or Python. And so now I have a whole lot of there are a whole lot of these functions. I think right now they're being documented in the documentation, but you'll find pretty much all the common functions that you have on Python or Scala collections. So on top of these syntax changes, a number of the other changes are more internals and only appear in the way you can load the data set. So a couple of them are AVRO, so AVRO support, better image support, and also reworked internals for the data sources. So essentially here, so in the case of AVRO, you can simply load AVRO files without needing some external libraries. And the point is that it looks like it looks very simple. This is the whole point. You can directly load AVRO, and this will work with structured streaming, batch, and macro batches. So you don't need to have an external library if you have that. This is the same thing also for reading images, which is something that for deep learning I've been very interested in for a while. So already in Spark 2.3, you could load images, but loading images was not integrated with the rest of the sources that you could read. So now you can directly use you can consider a directory as a place where you can load some images. So if you have a directory that contains a lot of JPEG images or PNG images, you can ask Spark to load all of these directly as a data source. And this will work also with streaming and with and with microbatches. In particular, in practice, some good options which turn out to be pretty useful are exploring recursively all the subdirectories. So if, for example, if you have a directory containing cats and another one containing dogs, you can simply point to the root directory and it will load everything for you. So for people who are more deep into the internals, and if you write your own source, your own data source into Spark, the internals are being significantly rewritten. So already as of Spark 2.3, there was already a new API that to express how to write a data source. This API was written to address a few limitations that we had with the original data source API. And this API was meant to allow you to have a more complex integration with the Catalyst engine so that you could have predicate pushdown. In particular, if you are writing your own engine, you want to be able to have the information that Spark is going to filter out 90% of the result, for example. You want to have the information that Spark is going to just collect a specific range or specific key of all the data set. So data source v2 was addressing these concerns. But people found out, but it was found out that people had actually had some hard time to use this API because it was combining a lot of things together. It was combining Catalyst information. It was combining the way to read the data, so low-level bit manipulations, and so even now we are optimizing this API so that you can break down what you are doing with inside the data source into multiple pieces. So one piece is more dedicated to loading the data. Another piece is dedicated more to passing information from and transforming the logical plan that you are getting or the physical plan that you are getting from Spark. And another piece is is able to expose the metadata. So the final API is still under discussion, but this is definitely an area where the support from the community was particularly helpful. So this is, I would say, the general changes inside Spark. One of the big changes, especially in terms of machine learning and deep learning, is all this work being that is laying ground to being able to integrate much more deeply the Spark with all the AI frameworks. So I guess most of the people here use Spark for doing either traditional ETL and data transformation, or for using MLlib and applying some of the machine learning models, I presume. I presume most people here don't use Spark for doing deep learning. Is there anyone who is using Spark with deep learning, apart from me? Okay. So typically when people want to use deep learning, typically they use a completely different setup, and they are struggling to pass data back and forth between the deep learning stacks and Spark. So what we found, so what we found out is that typically, people have their data coming from different sources. They do some preliminary data transforms, and then they train. When they want to train some deep learning models, it is done with separate frameworks, and there is definitely a gap to go between the two here. So this is what Project Hydrogen is addressing. So why would you want to combine these two worlds together? So you can realize. So one realization that has been clear, I think, from the last year, is that the community of AI and the community of big data are actually converging toward the same set of issues and the same set of solutions. Because if you look from the perspective of AI, if you want to do AI these days, you need to have usually a large amount of data. Especially if you want to if you want to train an image network, typically these networks are much more complex and require much more data in order to be effective. And this is why you see inside TensorFlow, for example, or inside the other frameworks, you see that they are starting to develop their own ways of transforming the data, because they realize that in order to be effective at building some deep learning model, they need to do a lot of data transform, and they need to be able to address these data transform problems at a large scale. which is really what Spark has been solving for quite a number of years. On the other side, if you're working with, if you're already using Spark, or if you're already working with big data, there is clearly a need to be able to integrate with existing deep learning frameworks. Because inside your pipeline, you eventually have a step where you apply a machine learning model or you apply a deep learning model, and this is where you want to be able to integrate Spark with some of these machine learning frameworks. So there has been already a lot of efforts done in this space. I think Yahoo has been leading the efforts initially with Caffe on Spark and TensorFlow on Spark. Databricks has published a number of packages that address different problems. And I think all in all, we counted on sparkpackages.org, I think we counted about 80 packages implementing an algorithm or dealing with integrating an existing library with Spark. So when we looked at how to integrate these two frameworks together, we found that there were two big problems overall. One of them was data exchange. So if you have your data in Spark, how do you pass it to TensorFlow, for example? The other one is execution model. So the problem here is when you run TensorFlow, TensorFlow needs to run in a way that is different than what Spark expects. So more precisely, if you look at the problems that it is solving, Spark works by chunking its work into multiple independent tasks and then running each of the tasks independently. Well, if you look at how distributed training works, distributed training typically assumes that it is training one model and that this model needs to be shared in a coordinated fashion across all of the machines in a cluster. And this requires tight coordination between the machines, which is really the opposite of what Spark assumes here. So in a distributed setting, you need to pass gradient information, or you need to pass more information across all the machines when you have a distributed cluster. So Spark assumes that if one node crashes, then it's simple. You rerun the task, and eventually it will complete. But in the case of distributed training, this is a completely different problem, because in distributed training, you cannot simply spawn again one node and hope that it is going to coordinate itself with the other nodes. You need to stop your computations and you need to restart from the latest checkpoint that you have been doing. And if you don't do that, you will typically introduce some biases inside your model. So you'll get different results if you have one node that crashes and you don't take care of restarting from a common checkpoint. And of course, this is not how Spark was designed to work. So Product Hydrogen is addressing all these issues of scheduling and of data exchange. So it's really actually three pieces. One of them is what I was mentioning about improving the scheduler. Another one is the optimizing the data communication. And the last one is presenting to Spark enough information about the hardware so that it can make decisions for scheduling the tasks that require specific hardware. So here is what it will look like in practice if you want to write your own deep learning code. So the technique of having coordinated tasks this way, in which you restart everything if something goes bad, is called in high performance computing is called gang scheduling. Simply because it's assumed to be working like a gang. If one cooperates with the police, then everybody else cooperates with the police, or nobody cooperates with the police. So this is not new. This is something that the HPC community has been doing for a few decades. But now we are adding that into Spark as another scheduling option. So the way it works inside Spark is that if you ask a job to be executed in this mode, then all the tasks are going to get started together. And they will have enough information to coordinate work between each other, in particular to stop all at once if they need to do some work that needs to be done before they can move on. And if there is a failure, then all the tasks will get cancelled, and then they will get all restarted on the remaining executors. So if you want to write it, this is what it looks like in Scala. So you would specify at the RDD level that you are going to go, that you want to have a barrier for the RDD. So you get a special RDD here, and this RDD is going to wait for enough slots to be available, and then executes all the work on all the partition at once, and then we'll wait for all the work to finish on the final partitions. And inside this function, so this is not your regular map partition. This is a specific re-implementation of map partition in the case of a barrier RDD. And in that case, you can have extra information about the other nodes. In particular, you can have access to the IP addresses, how to communicate to them, and so on. Another piece, yeah.
What happens if your game-changing job has more tasks than executors you can actually have in your cluster?
Yeah, so if you don't have, yeah, that's a great question. If you don't have enough slots in your computation, and you ask for more slots, well, simply it will not execute. At least the design decision for now that it will not execute, because typically because you want all the tasks to be able to execute at once when you are in this mode. Otherwise, actually, and here you will see why with this barrier, with this concept of barrier here. So typically, when you want to use deep learning, you expect to do some checkpointing and you expect to do some coordination operations. And when you do that, you want to be able to wait on all the machines for one machine to complete some work. Typically, if you have a master node, and then wait for this master node to write some checkpoint, and then the other nodes can complete and then read this checkpoint and then continue. So typically, this is done when they need to exchange some gradient information, and then once all the gradient information has been sent around, then the cluster knows it can proceed because all the machines have received all the information. And if you were not to have enough slots, then essentially you would be blocking forever because some of the tasks would not have started and would be waiting. So, and the one that have started would be waiting for the one that haven't started. So, I think for now it will simply not even proceed. But I think here there's a design decision for whether we're allowed to proceed or not, and be a bit more graceful in case of degradation in that respect. And so typically, actually, what we found that the way it works that if you have a master, so the master will get the information about all the other nodes. Then it will send some either through SSH or through some other mechanism. It will trigger some MPI jobs, or it will trigger some remote TensorFlow jobs on the other machines. So Spark doesn't even know that something is happening on the background. And then all the node will wait for this TensorFlow or MPI jobs to finish, and then everything else finishes. So this is really why you need to start everything at once, because the master will assume that all the nodes are available when it does that. And of course, in order to be able to do that, here we say, let's get all the addresses of the task. This is not an information that right now is exposed inside Spark officially. And this is where we need some more coordination from the cluster managers under the hood. In particular, what we found is that people want to establish SSH tunnels between the machines to securely schedule and trigger some work. And right now, this is not something that is exposed. You cannot, inside Spark, say, hey, I want to have an SSH tunnel onto another machine to be able to launch some commands there. Spark has its own way of submitting data, and this is another way that needs to be added at the cluster manager level. So at this point, we're working with the communities of the most popular cluster managers to make sure that we can address these problems to help help the development of distributed training on top of Spark. So another piece which was particularly critical was how to communicate data, because if you look at this code here, you start from an RDD, and then that contains your data, And then you want to be able to take this data set, all this piece of data, and then run some training jobs or run some inference job against these. So, before that, it was not. So it was really hard to communicate data in an efficient manner. So most of the code that you use for doing deep learning, for example, is written in Python. And if you want to embed Python code inside the pyspark, the standard way to do that is to use a user-defined function. And this is how, for example, you would embed TensorFlow inside Spark. That's one way to do that. And if you know how Spark works, you know that it will take each of the rows that it stores internally, and then it will pass each of the rows, send one of the data point send the relevant data to Python. Then the Python process will return the results. Spark will then join the result back into its row, and then store the row for further processing after the UDF. And then it would do that for each of the rows, and complete afterwards. So if you do that, row by row, this is the kind of performance that you get. Essentially, you spend between 95 and half of your time simply passing data back and forth between Python and Spark. It's really inefficient, especially for numerical data, which tend to be very compact, and for which Spark has simply it's mostly overhead when you want to send data. So now with Spark 2.3 and even more with Spark 2.4, you have access to this is what people call the pandas UDF. You have access to data in blocks and directly inside your UDF. So the way it works is that you express your transform by saying not instead of taking a row, but by taking a whole pandas data frame. And Spark will send to you the whole chunk of data at once, which will amortize the cost of sending this data between Spark and between Python. So so all the cost that was incurring when one row was sent now is being shared across all the elements. So one of the big differences I would say between nowadays is that we are standardizing on one format, on one universal format for sending this data, which is based on the AVRO project. So the AVRO project is essentially a collaboration between Pandas, the NumPy community, and Spark and other communities actually for having a one standard way of sharing this data and passing this data across multiple software stack. So nowadays, you can even have, so here, this is using Pandas Python UDFs, but you could have other frameworks directly written in C or using BLAS in Java, and they could directly access the data in a low-level fashion using this standard format. So the way you would, the way you would use that in Spark, and for example, here this is in Scala. This is not in Python. You can declare your data frame or your RDD to be an AVRO RDD, and when you do that, Spark will represent your RDD as chunks of vectorized and contiguous data in memory, and then we'll pass this data set batch by batch, and each of the batches will follow the AVRO format. So here you could optimize your code with low-level code if you wanted to have quick computations here. So of course, what kind of performance games are we talking about here? I think we did some calculation, and in some cases, especially when you reduce the data, you can talk about 100 times faster code just by switching from something that you write manually using the regular Python operators to something that calls the pandas operators, which are heavily optimized and rewritten in C. So in that case, you can, if you're dealing with numerical code nowadays, I strongly encourage you to switch to the new pandas to the new pandas UDF for several reasons. One of them is that typically, you will, I tend to prototype first in pandas for numerical code, and then I try to adapt it to Spark. And here, that means everything you do in pandas, you can directly embed it inside Spark. You don't need to rewrite it. And you will have also the added benefit that with Spark 2.3 and 2.4, you will have just as good performance as you had before in pandas. So you have hardly any overhead anymore coming from Spark when you want to deal with numerical code. So I wanted to quickly show you what it looks like in Spark 2.4. Of course, this being a live demo, it never works, but who knows? So I guess can you read from the back? Okay. So here I have a GPU cluster, and this this GPU cluster is running on Amazon and has a P2X large GPU machine, so one GPU per machine. And here I'm going to run. So I'm going to I'm going to show you what it looks like when you run. When you run Spark 2.4. So this is using a preview of Spark 2.4. So I have here one notebook, which I'm going to start here. So this notebook is going to run a distributed Horvath training session. So Horvath is a framework from Uber that allows you to take some TensorFlow code and distribute it across multiple machines in a synchronized fashion. So it's a very good candidate for if you want to do distributed training with Spark. So here I have, so the task I'm going to solve here is taking some digits and recognizing them for their value. So this is a standard MNIST data set. And as you can see here, so I'm loading my data. I'm asking Spark to repartition it into 2 partitions. So and also this is a fairly small data set, so I can easily do that. And I'm going to run, and because I'm partitioning it into two partitions, Spark is going to launch 2 tasks using barrier mode, and it will then use two of the nodes of my 4-node cluster to do some distributed training. So 2 of my nodes in my cluster will be used to do distributed training. And the code here, so all the deep learning code is actually fairly standard TensorFlow code, which you can directly embed inside by mapping over partitions here. So okay, so I launched my Spark job, and as you can see here, it's launching two tasks, and since it takes a while, it is right now running in the background. So while it is running, what I can do is, this is Spark. So nothing prevents me from using the model that is being created by this model, and then check in real time using streaming to see what is the performance of the model against a stream of incoming digits. So what I have, so the other notebook I have here, let me start it. So this notebook here is going to read a subset of this data set, but it is going to read it as a stream, and it is going to load the model and use this model to run a prediction against the features using the GPUs. So all the codes, all the tasks here are going to use the GPUs. So these 2 nodes here, I'm using 2 nodes here for running GPUs, and here on my stream, I'm going to load as much as I can, even if it has more partitions. I'm going to try to run as many tasks as I can to use these GPUs. So one thing that you would notice here, that actually Spark is aware that it will only have here 2 nodes available for running GPU calculations, because the other 2 are being monopolized by the gang scheduling of the node. So okay, so now I start to have some predictions. It looks more or less correct, but what we're doing here, that on the same cluster, I'm having here on one job that is doing some training using the GPUs, and then another job that is running on the same cluster and running and doing distributed streaming inference. So if you were to try to do the same thing with Spark 2.3, it would crash because Spark would not be able to figure out which nodes, which GPUs on which machine would be used for training and which one would be available for doing the inference. Now that Spark is aware of how it needs to split its work between the different machines, it can properly segregate these different tasks. Please.
Does this do this as well on Kubernetes?
So I think it should work on Kubernetes at this point. If it doesn't, it's a bug. Okay, how much time do we have still? 15 minutes? Okay. So this is what distributed training with GPUs and deep learning is going to look like in Spark. So actually, talking about GPUs, there's still a couple of things that will need to happen in Spark. One of them is making sure that Spark is aware of the hardware available. And as you noticed, I was using here a cluster with just GPUs on them. I was not having a mixed cluster with CPUs and GPUs. And that's one of the that's one of the common use cases. People tend to train on GPUs, want to do inference on CPUs, and how to be able to use the same cluster for doing that is right now is fairly challenging. So this is a proposal of an API. It is not available. So this is being discussed. It's not available. I don't think it will be available in Spark 2.4. But essentially, within the RDD, you will be able to specify the required capabilities on your hardware to the jobs that you want to run. And also, some tasks are able to fall back to CPUs when they don't have acceleration. So this is one of the options that is being discussed. And also, again, inside and nowadays, since you have machines which have multiple GPUs, Spark will be able to expose to the programmer which GPUs are being already scheduled by some parallel task on the same machine and which one are available for doing training, or for doing inference within a task. So right now we're mostly at this point. There is a prototype inside the standalone application, and now we're talking mostly with the different cluster manager to see how they can expose this information inside Spark. So this is still a work in progress. So in terms of a timeline for product Hydrogen, at this point, so everything I showed in the demo is going to be runnable on Spark 2.4 once it is released, and in Spark 3, which is tentatively the next version of Spark after Spark 2.4, you'll have also the accelerator-aware scheduling being added to Spark. Okay, so so this is it for Spark. So this is for the work on Spark. Another piece of another project I wanted to talk about is MLflow. I think we have time to cover that a little bit. Yeah. And oh, by the way, before I finish, of course, this project, Spark Hydrogen, is a community effort. A lot of people have contributed to it. In particular, it emerged from all the common needs from all the projects that were solving one piece of the puzzle, both on the Spark community and on the TensorFlow community in particular. So let me switch a bit gears here, and here we talked a lot about deep performance for accelerating some of the workloads. Now let's talk more about the high-level organization, about how you can take the work that you do into Spark and how you can more easily put it in production. In particular, when you have different tools and different teams organized that need to collaborate on that. So if you have done, if you have done production, if you have put machine learning in production, you probably found yourself having to work in this sort of cycle here. So you start usually with some raw data, then you have to clean these data sets to get it into some proper form. Then you can pass it to some machine learning algorithm, your favorite one. Then once you have trained something, you don't necessarily know how good it is going to be in production, so you're going to deploy it. And once you deploy it, you find some other insight. You find that it's not performing as well as expected. You realize that you need to go back to the drawing board, that the data you were collecting was not necessarily good enough, or that you needed to, or the preparation had some bugs, and so on. So then you need to, and then you start to iterate on the cycle here. But this is the theory. In practice, it's a bit more complicated than that. So why is it complicated? For each of these steps, you have typically some different technologies. You also have different parameters that you can tune. You know, when you do data preparation, should you drop some data? Should you remove the outliers? Should you keep them? What is an outlier? What kind of bucketing should you do? And so on. Same thing for training. And then, of course, all the problems that I'm talking about are getting magnified once you move to large data sets. So this tends to be becoming fairly complex to manage overall. So MLflow is coming also. One of the pieces that we found was tended to be lacking is once you have trained a model, how do you make sure that this model is properly exchanged and kept track of by your system? I've had to talk with some Spark users who told me that they deployed a model in production and then they didn't dare touching it. They couldn't do anything because they forgot how they built this model and they could never replicate the performance of this model. So then they were stuck, and then they said, okay, well, now we don't touch it, and we just moved on to other projects because there's nothing we can do to improve the situation here. So MLflow is meant to address these issues. MLflow is a new open source project from Databricks that helps you manage the whole lifecycle around keeping track of your experiments, of holding your models and authoring your models, and keeping track also of how you ingest your data from raw data straight into building a model from it. So it has a couple of components. One of them is tracking, so making sure that when you run some experiments, for example, when you want to improve the click-through rate, if you are working in tech, making sure that you can record all the relevant artifacts so that you can replicate the experiment. These experiments then lead to a project. So a project is essentially a format, a package in which that contains everything you need to run the model that you produce onto a different platform or onto a production system. And these projects encapsulate models, and so these models are essentially the pieces that get produced by the different frameworks. So MLflow allows you to start from either notebooks or write applications, or even send some remotely some experiments, all into a server that is separate from your application, so that from the perspective of the user, you have a very small API that you can use, and all the artifacts that you produce are being tracked by a separate server on which you can track the performances of your model, and you have on which you can see on the UI how your experiments are performing. So let me show you. I think the best is if I show you what it looks like instead of explaining how it works. So just to show you what so this is an open source project. So you could install it from PyPy. And here, if I wanted to run this demonstration, I would also use scikit-learn and the matplotlib to generate some images. So the way MLflow works is pretty simple actually. All you do that you write your usual experiment code, And on top of that, you're going to also load MLflow for doing some, for tracking your experiment. So let's say that your experiment depends on one parameter here. Actually, let's say that your experiment depends on two parameters. One of them is going to be and these two parameters are going to be what you need for doing elastic net descent, elastic net training. So if you write your once you write your standard training code here, you would write a function that takes your data and take a couple of parameters that you want to be able to tune. And then inside this function, you would write your standard machine learning training code. So you would split your data here. We're going to do cross-validation to evaluate the performance of our model. So I'm going to split my data into testing and training. Then I'm going to keep track of the experiment while it is being run. And this is where in all this block, I'm going to have a standard set of elements that I'm going to keep track of within the experiment and within this run for the experiment. So after that, this is all your standard scikit-learn code. You would declare an elastic net regressor here. And then you would train it and then build some evaluation metrics out of that and log these evaluation metrics. So instead of printing these evaluation metrics like you would do, and then of course forgetting which one are being good, well after doing a couple of runs, you are going to ask MLflow to log all the outputs of your run. So of course we're going to log the parameters that we use. And then we're going to log we're going to log the performance that we got out of it. So here are a couple of metrics. And finally, we're going to log the model that we produced out of that. And since we want to see what it looks like, we're going also to keep track of a couple of other elements. Here, an image that is going to explain to us what it does. And this is something that you could run. This is something that you could run locally. You don't even need to have MLflow for doing that. So MLflow could run also without having a special framework. But where it gets interesting then is when you connect it to the server. Inside the server, it is going to keep track of all the elements, of all the parameters against which you run your experiments, and also all the metrics that you may have logged after that. So when you start to do that, you can start to compare the experiments. For example, you can start to see how each model performed, and then figure out the trade-off between the different model, and also you can decide if you have some good models, you can decide to deploy this model in production. So from the command line, you can then keep track of this experiment and then push it into a serving system if you want to. So far, the serving system that have been added have been Azure ML, SageMaker, and also you can try it locally on your laptop using a Python server. So, and then from this serving system, you have access to their own set of metrics as well. So MLflow is really meant to help you take the code that you have, and through adding a couple of metrics and through tracking a couple of through tracking your experiments, you can have one repository of all the experiments that you run, and decide then what is going to be good, what can go into production, and what can get discarded because it was just because this experiment didn't pan out properly. Okay, so this this is what I wanted to talk about quickly about for MLflow. Do we have? I think we have time for a couple of questions.
Yeah,
probably.
1 or 2 questions.
Yeah. Please.
I was wondering how this ties into things like Apache Atlas integration. So because it seems a little bit standalone, while if you deploy this in an enterprise place, you're never standalone, so you need to integrate with other things in the meantime. So I like the MLflow part of recording the metrics, but how to track those metrics across the enterprise is, I think, or across a company is more important. Where Spark is not the only thing that's running there.
Yeah. Once you have your model is only one piece. Then you want to be able to track the performance of your model not only across time and then across multiple experiments. Yeah, and so for doing that, yeah, that's a great question. For now, we have been mostly through the MLflow part, we have been mostly focusing on people who like to do data science either close to the laptop or on a server that they launch that is dedicated for that. And for it, they won't need to keep track of all the artifacts that they run but they tend to be fairly isolated when they run the experiment, and then they ship it to another team. In a larger setting in which you have a much more complex pipeline, yes, there is.
What I would expect is then that you would record those settings within the flow that if you're publishing a Docker container, for example, you store the metrics and the things that you need to redo the model inside the Docker container.
Yeah, so one thing which I didn't mention is that when a run is being done, MLflow will record, where is it? MLflow will record a number of information, including, if you're using Python, the whole conda environment that was used to rebuild that. And so far, we haven't added extra metrics like the one we have mentioned, but the one that you have mentioned. But yeah, this is something that I would love to hear more about. Please. So is your question about what? So if I understand correctly, here it's yes, I'm saying alpha and then I'm spitting for alpha. But here I could make a mistake and say this is alpha, but I'm going to supply L1 ratio, for example, and then of course this is not going to correspond to that. Or simply ignoring it. Yeah, that's a great question. And I was talking about it with one of the users. In Python, you can definitely do a lot of rewriting this way. For now, at least at the first version, we wanted something that was explicit in the API before going to something which is much more implicit, but also much more magical. And when it breaks, people tend to have a hard time to understand what it is doing. But definitely, this is something that, so I think so far with version 0.7, we have mostly focused on adding support for Java and R, but we're looking at how we can improve the support for Python too. This is still, I would say, a beta release in the sense that some people are using it for doing production data science, but the API is not finalized yet. And this is definitely the kind of thing that we're exploring. Yeah.
Last question, maybe.
Last question. Last but.
The MLflow feed in a more kind of DevOps tooling and the ecosystem, because I do understand that kind of logging and comparing, but to me personally, that whole kind of deployment, in one line, it serves probably very basic purpose, but in reality, the model, as someone said, is not the only thing. So the whole kind of release pipeline, it's way more complicated than just pressing one line. So how that should fit together with kind of the DevOps perspective.
Yeah. So this is so if I understand correctly your question, this is good for simple cases. When you are in a large enterprise and you want to have a more complex QA processing when you want to deploy a new model, how does it work? Yeah, that's a great question. From my personal experience, each enterprise seems to have its own way of assessing the quality of a model before deploying it, which is why if you look at the model, actually, what you get is a a directory with a number of stored artifacts, and if you want to, you can you can directly introspect the content of these artifacts here. One thing that we would hope coming from this project is at least a discussion on how to standardize the representation of a model. for machine learning, because there's a lot of effort around that. There is PMML, which is probably one of the oldest and most established ones. There you can think of scikit-learn with the pickle format, when it is pickle as being another format. Each of the different machine learning framework have their own way of representing deep learning networks. I think TensorFlow has at least 3 from my knowledge. So the question is more, how you can take all these models, which tend to represent the same thing eventually, and how can you have a common package for deploying them and assessing the quality of these models, especially when we are moving in a world where containers are going to be the unit for deploying these models. So I hope this. So I believe that MLflow is a step in the right direction. And we hope that we can build enough community support around that other frameworks are going to pick it up. And then it is going to be much simpler to add automated QA systems that are going to be standardized around that. But there's definitely still a lot of work to do for addressing the enterprise needs in that respect.
What do you think about Combust MLeap?
Yeah, so yeah, Combust ML. Yeah, we have been talking for a while with the folks at MLeap. MLeap has been working. I think that one of the differences that MLeap has been focusing on taking a model and building straight a container from it. Here we're trying to abstract a bit the problem and think, okay, not only you want to deploy this model, but also you want to address, you want to do a lot of QA preprocessing, as this gentleman was mentioning before. And you cannot simply go straight from something that you build to something that you deploy. And this is where having a standard container format, well, I don't want to use the word container here, it's very loaded, but a standard format for holding these models before pushing them is very relevant.
Joining hands with Project Platinum Vocal?
Which project?
Project Platinum.
I don't think I know about this project, but I would love to talk about this. Is actually where I think two questions beyond.
After this talk. So Tim, I want to thank you for speaking today. So because it's GoDataFest, we more or less stole the name from Oktoberfest. We have a bottle of beer for you. I hope you like it.
Thanks. I mean, you realize that I'm flying tomorrow, so
okay,
I'll have to.
There's a Databricks colleague here who's willing to take it over.
This is going to be a very happy night. Thank you.
Yeah. Thank you. So we'll have a